Imagine yourself in a university chemistry lab, undergoing a standard procedure for your PhD project, when suddenly you realise you've accidentally made an excessive amount of one of the most dangerous explosives known to man. An explosive so unstable that people call it the mother of Satan. Its explosions are known to be about 80% as strong as TNT, and even more sensitive to the slightest impact or shock. Its name is TATP, or triacetone triperoxide. This was the exact position that one student from the University of Bristol found themselves in February of 2017. And if it wasn't for the chemist's knowledge of reactions and chemical bonds, this could have been a complete disaster. In this video, we'll delve into fundamental chemical concepts that are crucial to develop your understanding of organic chemistry. We'll be covering peroxides, radicals, and the chemistry involved in producing TATP. So believe it or not, radicals and peroxides actually play a fundamental part in our everyday lives. Peroxides are both sterilants and antiseptics. So you can probably find peroxides in your cleaning products in your kitchen or also in the bathroom. They're also used in hair bleaches and for fuel. So understanding how they work not only gives you a more informed approach to chemistry, but also allows you to have a safer lab environment. So to understand TATP, we must first understand peroxide bonds. Peroxide bonds consist of a single covalent bond between two oxygen molecules, leaving each oxygen with one other valence electron, which can form another bond. As you can see, TATP has 3 of these bonds, as indicated by the T, which stands for tri. Now, these bonds are unusually unstable and reactive for a covalent bond, and this is the reason that a lot of peroxides are actually very, very unstable and hazardous. One you've probably heard of, which is the most simple peroxide, is hydrogen peroxide, so the R group over here is just an H. When the oxygen-oxygen bond breaks, this is called the decomposition of this molecule, which usually happens by a process called homolysis. Homolysis involves a bond breaking where each molecule retains 1 electron. You may have heard of this before because it's a great way to form radicals, which are molecules with 1 unpaired valence electron. So an example of this is when hydrogen peroxide is exposed to light and the oxygen-oxygen bond is broken. So if we break this bond in the middle, what do you think will form? Well, the answer is we'll form 2 of the exact same hydrogen peroxide molecules. 1 electron is given to each of the molecules, which gives us 2 OH radicals. The OH radicals can go on to do all sorts of crazy chemistry. They're actually a really important part of our atmosphere. But why do bonds break in this way? Usually when we draw a bond breaking, we draw it with a double-headed arrow and both electrons move to the same place. Well, we actually have to use single arrows in this case because the radicals that are formed at the end are actually more stable than if we were to form 2 charged species. So given what you know now, can you draw the mechanism for OH radicals and HBr? This is the second initiation step for the radical addition of HBr to alkenes. So following the same process of homolysis that we did in the first initiation step, the radical attacks the hydrogen and the single bond undergoes homolytic cleavage. We represent these as single-headed arrows, and this produces water and our Br radical, which is essential for our next step. This Br radical can change the outcome of reactions. More specifically, it can change the regiochemistry of the addition of Br to alkenes. Regiochemistry is the preference of a chemical reaction to occur at a specific site within a molecule. So what normally happens when an alkene reacts with HBr without the addition of hydrogen peroxide? Usually when you add HBr to an alkene, the Br will add to the most substituted carbon. This is known as Markovnikov's rule. So we draw our arrows from the area of electron density and attack the delta positive H, leaving the bromine with both of the electrons from the covalent bond. So why does the Br add in this way? Well, it's because the secondary carbocation is more stable than the primary carbocation. And here's why. Because the carbocation intermediate will be stabilised by the inductive effect of 2 CH3 groups instead of just 1. The more carbon groups attached, the more stable it'll be. So after the H is added, then the Br adds to the most substituted carbon. This is called the Markovnikov's rule. The hydrogen atom always adds to the carbon with more hydrogens. We can get completely different results if you simply add H2O2 into the mix. Instead of Markovnikov, we get anti-Markovnikov addition to Br to this alkene. Given the first 2 propagation steps, can you figure out how these 2 molecules will react to the alkene to give an anti-Markovnikov product? And a little hint for this is that the process undergoes homolysis starting with Br. If you suggested that the Br radical attacks the alkene first, like so, to produce this radical here, then you're right. This is because radicals are electron-deficient species and are stabilised by adjacent electron donors, very similar to carbocation intermediates. The more stable free radical intermediate is the tertiary free radical. and therefore the Br addition occurs predominantly at the less substituted carbon. This is very useful in synthesis of important organic compounds as it allows for regioselectivity. So even though this molecule might look simple, it's actually very unique. And that's not all. Just by looking at this molecule, do you think it would be an electrophile or a nucleophile? Well, if you answered either of those, it's correct. Hydrogen peroxide can actually act as a nucleophile and an electrophile, depending on the reaction conditions. Because if you look at the structure, we have two oxygens next to each other, both with lone pairs, which can attack an electrophilic site. This is because of the electron density in this area. The electrophilic site could potentially be a carbon in a carbonyl, for example, because this was the first step in the disastrous creation of TATP. So I'm going to walk you through the first step of this mechanism to demonstrate how hydrogen peroxide can act as a nucleophile. So in order to form our first intermediate, we must start at the site of electron density and draw our movement of electrons from here. We know that the carbonyl carbons are delta positive because the electron density is focused on the electronegative oxygen. Therefore, our molecule can attack like this. The next step is a hydrogen transfer from here to here, and that leaves us with our first intermediate. So can you complete the next stage of this mechanism? Add another equivalent of acetone. This therefore forms dihydroxypropyl peroxide. So pause the video here and see if you can figure out how these two molecules react. Just like the last mechanism, we attack from the lone pairs on the oxygen, as this is the site of electron density. We push the electrons from the double bond onto the electronegative oxygen to form this charged species. Then we do a hydrogen transfer to form this final intermediate, which has two alcohol groups and one peroxide bond. This intermediate goes on to react with another molecule of hydrogen peroxide and then undergoes cyclization to produce TATP. So now we know more about TATP, peroxides, and how it's formed. What does this mean for our student in the lab? So after the student notified a member of staff over what they'd done, the department immediately took action and evacuated the building. Soon enough, there were 4 fire engines and the Avon Fire and Rescue Services attending the incident. But why was there such extreme measures taking place? Surely if the student had synthesized this compound by accident, how could there be so much of it being made? Well, it turns out that this student had added hydrogen peroxide to the acetone in their reaction mixture as part of a completely different safety measure. Despite there being safety briefings against this, the student had created almost 30 grams of TATP, when 1 gram is capable enough to be a deadly explosion. So what was their plan of action? If the substance is sensitive to friction, heat, impact, and static electricity, on top of the fact that TATP can even explode underwater, at about 7 p.m, the Army's Explosive Ordnance Disposal Team carried out an explosion to remove the substance from the building. No one was harmed, and the university could go back to normal. So despite their destructive tendencies, peroxides are a very important part of chemistry, and understanding the way that they work unlocks a multitude of different uses in everyday life, and could potentially prevent an encounter with the bomb disposal team.